So welcome to lecture 4 of the machine learning and pattern recognition class. And today we'll talk about two things. We'll just finish the non-parametric methods for density estimation, and then I'll talk about nearest neighbor classification. And this lecture is put together this way because well, you'll see that nearest neighbor somehow is related to density estimation. And if we come up, and this will be the core of the lecture today, with a classification method, which is actually quite classic, like very popular 60s, 70s nearest neighbor. And we say it is good to classify using nearest neighbor. It must be somehow related to the theory that we talked about in the first two lectures. Like if I have joint probability, or if I have conditional probabilities, in Bayesian decision making, the optimal decision is for the maximum a posteriori class. And I cannot now switch and say, well, now we'll look for the nearest neighbor. So these two things must be related, or we are not doing the optimal thing. And that's why it's good to speak about, see the relationship between nearest neighbors, density estimation, and then explain the recognition method. Okay, so just a short recap from last week. We talked about parametric methods for density estimation, and the advantage is that they have low number of parameters to estimate, and some of the methods are very easy computationally. But the disadvantage, which is a very significant one, a major one, is that the resulting estimated density can be arbitrarily wrong if the underlying distribution does not agree with the assumed parametric model. So if we assume the distribution Gaussian is in fact normal, then we can run into problems. And today we'll touch two methods of non-parametric methods for density estimation, just to connect the last lecture with this lecture. So let's have a look at this slide, and we have an example here. So let's assume there is a distribution Q of X, its probability density, because it's real, and it's a mixture of two Gaussians. Normally, of course, when we are estimating a distribution, we have just a sample. So, but we don't have the distribution. Here we'll see the ground truth, so-called, what we are supposed to estimate to see how good certain methods are. Now, then the estimation is really based on a sample. Here we'll take 1,000 samples generated from QX, and the histogram we'll look at it as a piecewise constant estimate of the underlying distribution Q. So QX is the ground truth, PX is our estimate, and the function here will consider the bin locations as fixed, and the only parameters we will be estimating would be dB, which is the probability density which has been assigned to bin number 1. D2 is the probability density assigned to D2, and so on. Now, because this is a probability density, it has to integrate to 1, and we can calculate the integral as a sum over the bins, and in each bin this is a constant function, and we get this condition that the sum over all bins di divided by b has to sum up to 1. Okay, now so first we'll try a method that we talked about last week, one of the methods, and this will be maximum likelihood. So let's see. The first thing I would like all of you to understand is Formula 2. So what is the likelihood of the sample or the training set T, which are the N was 1,000 in the example before, points, given the parameter theta, the parameter vector. The vector has all these DIs, D1 up to dB. This is the density in each bin. So the likelihood is a product of the probabilities xi given theta, we are invoking the principle of independent samples. So someone independently generated these 1,000 points. And because we know the probability is constant, we can do the product over all bins and over number of elements that fell into the bin nj. So the probability, if a sample falls into bin j, the probability density of that observation is dj. It's the same for all the points. So we have dj to the power of nj number of points in the bin nj, and we have to do the product over all bins. So do you understand where this? This question could come up in an exam test. What is the likelihood of a data set x1 up to xn for a piecewise constant distribution where you have b constant segments, each with density dj? So that would be the answer. Now, we have said last time, we've said already that if we want to maximize some function, we can maximize its monotonic transformation. And here, taking the log of the quantity equation 2 is much simpler. So the product becomes a sum, and the nj log dj to the power of nj becomes nj log dj, and we have to maximize that subject to the sum of the densities times b going to 1. And now we'll solve this as constraint optimization using a Lagrangian multiplier. So that's used, this is the quantity we are minimizing plus lambda times the constraint, and we get the result, which would be expected that it's nk over n, and b is just a normalization factor. So nothing really spectacular here. Now, let's have a look at the result that we'll get for this particular sample as a function of the number of b's. So the number of bins, this is something that the user typically has to provide. And let's have a look at these graphs. So first, the question. How would that graph look like if the number of b goes to infinity? So what will be the decay? How will the decay look like if we had a very, very large number of bins? How would it look like? So we have the biggest, the largest number of bins for this sample of 1,000. What we considered was 4,000. That's the bottom right corner. And
most of the bins will be empty as we have finite samples.
Yes, and what about the others? So most of these will be empty, so that's 0. Oh yeah, I forgot to switch. I'm drawing something on the paper and I'm not showing it. Yeah. So okay. So if the number of bins goes to infinity, the decay, most of those will be 0. And what about the others?
Well, the weight has to go to limit to 0, so they will have to be
No. So let's say we have a very large number of b, and we have n equals 1,000. So most bins will look, so maybe, okay, b minus n bins will have a 0, yeah, because we have n at least, yeah, at least. And what about the other? So we'll have like the nk, maybe it's better to write the nk will be 1 for the others, because as the bins get very, very narrow, it becomes extremely unlikely that 2 points will fall in the same one. So, but now, so we see that B is not like going for infinity. It will say, well, so the density function, if we estimate it with very big B, it will be like high nothing, high nothing. It will be like 0, 1. And that's very, very far from the ground truth, which you see as the red curve. So any idea how B could be set reasonably? So which B would you choose based on these pictures? That you see this, what you get, the estimates. Or some idea how to do that?
I believe there is a fixed number of, like, there's a constant that you can multiply the bins with to get the values, but I'm not sure which one it was. I forgot it.
Okay, no. Okay, so okay, so what we see, well, maybe this is a too difficult question. One thing that you cannot use the maximum likelihood principle, because the likelihood of the the likelihood function will grow with the number of bins. Yeah. So this is a difficult topic, so we'll have to spend some time on it. So okay, let's maybe start with the bottom part. That's very easy. So let's see what happens just empirically. We'll do an experiment. Start. What happens on this sample if we consider the distance between the true distribution, which is Q of X, and our P of X, our estimate, and we'll make the quadratic error here. And we'll see that the nearest will get somewhere around 30, which if we look at the estimate, it sort of looks the best as well. But it's more common in machine learning to use a different distance between, it's not a distance because it's not symmetric, it's called divergence, the Kullback-Leibler divergence, which has also the property, maybe I will write this Kullback-Leibler on the paper. So we have plus minus infinity, but in our case, this is actually only from 0 to 1, log px divided by qx. And that's the same thing as integral. Actually, whether I write the integral first or second, px log px minus px log qx. And I will write here a bracket like that. Okay, so the property of this, the Kullback-Leibler is 0. So the important thing about Kullback-Leibler is that the minimizer, so dkl is equal 0 only if px is equal qx. That's the same for all the points. That's the same thing with the SSD, but it has a different interpretation. And one way to interpret it is like, does this formula is this one? Does this formula remind you of something? So this is the entropy of the px distribution, and it's also the shortest code length with which you can code messages which are generated with distribution px. And this one would be the coding length for some suboptimal strategy of assigning codes qx. Of course, here we say integral of qx equals 1, and the same thing for px, because these are distributions. So it has a better sort of statistical interpretation than the sum of square differences. But the important thing is that here you see again the Kullback-Leibler distance between the true distribution, which we happen to know, and our estimate is somewhere optimal between 20 and 40. So let's have a look at this a little bit more carefully. So the first thing, it shows that we show here on our particular experiment that the maximum likelihood estimate is not, you cannot use maximum likelihood principle to choose the number of bins, because the larger number of bins, the higher the likelihood. And it's sort of, we looked at this extreme case and this is not good. I will make a small detour and I wonder what will you tell me about this. Imagine I draw 4 points somehow like that. And I ask you, should I fit a line into this? If someone wants to estimate maybe this is time, and you would like to make a prediction what happens next. Should I fit a line to this, or should I fit a parabola? Which would you prefer, and what do you think, which one is better, and how would you justify that choice? Any idea? So almost everyone knows that, okay, if we assume a Gaussian distribution of noise, the best way how to fit the line is to use the least squares method, and you know how to do that. But the question is, okay, Matis, I can't hear you. Maybe there's some, try to say it again.
Sorry, I had an error. That wasn't real.
Okay, okay. So any idea how you would, how one would do that? So, okay, I'll tell you, and we'll use this principle for the histogram as well. So the problem, it's obvious, like if we increase, so one thing is obvious, we cannot use the residual errors, because if I have a fourth order polynomial, so if I use a high order polynomial, soon I will be able to fit all the 4 points. Also, a line which has one parameter here, or 2 parameters, okay, maybe A0. So a line is a special case of a parabola, and that's a special case of a third order polynomial. So of course the minimizer of the residual error on some set here for the line is a smaller, it's a smaller space than for the parabola, so the residual will be monotonically dropping. But we would like to introduce now a concept of cross-validation. So what you do is something like this. You pick one point, say this one, fit the remaining 3, and measure the error on the 1. So the 3 will get somewhat line, or on a parabola. The parabola will have 0 error, and then we'll measure the error on the left, so this would be a leave one out procedure, leave one out. Now, because the estimation, the fitting procedure did not see this point, the error on that point is unbiased, and then we can swap, hide this one, fit the 3 points, and measure the error here. So a special case of cross-validation is leave one out. You can have something like, if you have many, many points, you can split them into 2 groups, fit one, and measure error on the other one. And here we'll say the best model is the model which has the best predictive capability, and we'll choose the leave one out method. So for the bins, we'll say, okay, we'll hide 1 point of those 1,000 in the estimate, use the 999 remaining ones for estimating the parameters of the histogram, and then we'll check what is the likelihood of the remaining point that was not taking part in the estimation. Okay. Please write in the chat that you understood cross-validation and you know what how this operates. Or if there is a question, ask a question. Okay, good. So the idea is you cannot overfit on something that is hidden. Hide some part, fit the rest. Maybe you overfitted the rest, but that doesn't matter. We'll choose the model, the complexity of the model based on the error, on the points that did not participate in fitting. So let's have a look here. Okay, this is just the case that we already covered. This is explaining the cross-validation. We use the paper to do that. But here, so the cross-validation here ends up with 7. It gives us the result 7 bins. That's not too bad, but it's not too good. Why? Why did it stop at 7? So if as soon as we took more bins than 7, some point, okay, maybe I can draw it somewhere. So if you do cross-validation, it became with more than 7 bins, we were estimating if one of the bins gets no point in the test, so if D, say J equals 0, and then the cross-validated point falls in here, the likelihood of the cross-validated point, the point was not part, we took our points, and some points were participating in the estimation of the density, and one point was left out. And if that point falls into a bin which has 0 density, then the probability of that number of bin is 0, and for 7, more than 7, it happened. So okay, we get, if we look at this density for 7, it sort of does some approximation of the distribution, but we see that not from the Kullback-Leibler nor from the sum of square differences, it's not a good number. It's not a good choice. So what we could do is do exactly the same thing that we did for the flipping of the coin, when we're estimating the probability of a coin for showing a head or tail. And what did we do? We said, well, we have some a priori probability for the probability. So the probability of a coin being fair or showing a certain probability of the face and the rear side. So we call that pi. The probability pi was the probability of showing heads, and we made a distribution on that, and then estimated the maximum a posteriori. So here, the natural way to do that is to say, well, the probability of a certain, so this is maybe quite difficult to first understand. I will write it here. So we'll say, okay, this is a function of these parameters AI. So it's called the Dirichlet distribution. And what does it say? If I give you some set of alphas, I will give, this will generate a different distribution of D1s, D2s, D up to DB. So maybe a common choice would be AI equals 1, then the exponent is 1, and all, we will say all D1, D2, DB are equally probable. And Giving this prior, well, we'll have to get this alpha from somewhere. The map estimate becomes ni plus alpha I minus 1, and this is the normalizing factor. So you see that we stabilize the solution, and for the bias estimate, where we will get this ni plus alpha I over n plus sum of alpha I. So for instance, if ni is 0, actually the estimate is alpha I over n normalized with b. So we will not get this extreme case that certain for one observation which would fall into an empty bin would sort of make the likelihood 0. And for this for the Bayesian estimate, it turns out that we get 30 as the optimal result, which is actually the best one, a best piecewise constant approximation of the ground truth distribution. Yeah. Okay, so that's histogram, and now we'll switch to k nearest neighbor. So maybe it's not so easy to like not immediately obvious that nearest neighbors are related to density, but okay, think about 1D. This is the example that you see in the presentation. So in 1D, we can define the density estimate as probability of the volume in which we find the one nearest neighbor. So in 1D, it would mean the density at a point is the 1 over distance to the nearest neighbor, because the density is the number of elements, well, divided by the volume. If we keep normally we think about more as we are saying, okay, define the volume. Let's say the density of population in 1 square kilometer, and we count the people. But we can also fix the number of people and define the volume. Yeah. Now, there are results here for this. These estimates are a function of k, and you see quite peaky distributions. Does anyone understand why it looks like this? So I'll show it for 1D, and I think it will be clear. So imagine we have some set of points, and we want to estimate the density at a certain point x. So I will create some splits here. So within the green boxes, the nearest neighbor is the blue point. Say I will pick one, say this one. And now how will the density look like in that bin? So on the border, if this is D, the density will be 1 over D, and it will go actually to infinity, because here the density will be, the distance will be to nearest, and this function will be 1 over D. Now here we will have another 1 over D going to infinity, and so on, and so on, and so on. So it will be quite peaky. If you have 2 nearest neighbors, the peaks will not be so pronounced, but it's still there. So let's say we have some points here, and let's say if we ask about this point, x here, then if we start moving this way, the second nearest is still the same guy, is this one. So the distance, now what will be the value? So this is the distance d, and we'll be going 1 over d, and at this point we'll not have in the dense, sorry, it will be the other way around, yeah, 1 over like that, and this will be d2, this value will be 1 over d2. So we'll get this pk distribution because there is 1 over always. For k50 it starts to look reasonable, but still it's sort of quite noisy. So the nearest neighbor can be used for estimation. It is related to density estimation, but the density estimates are not smooth and they don't look nice, but we have seen the connection between nearest neighbor and density estimation. And fine. Now we have finished the part where of the whole course where we talked about models, it's optimal decision making, estimation, and we are switching to practically used methods in machine learning. So k-nearest neighbor is one of the oldest methods for recognition, perhaps second, third oldest, and it's still in broad use. So I will first define it, and we'll talk about properties and then focus on some improvements of the method. So k-nearest neighbor classification is mathematically not so easy to define, although probably every child would give you a definition. So you have in your memory a training set of examples, x1, k1, x2, k2, xn, kn. Think about beetles, or you have a collection of beetles. Everyone is labeled. Someone brings a new beetle. You go through the collection. You have a distance function. You compare your new beetle with every single one in the collection. You get a positive number, and the nearest neighbor is the class you assign it. Same with mushrooms, same with people, say gender of people. K nearest neighbor is only slightly different. You find K nearest points from X using the metric D, and the decision is for the class which has the majority in the selected subset. So in the top R. This might look like a weird notation. It's like if we want to know the value for L, we are going through the K top results from the nearest neighbor sorting, and L get this is called an Iverson bracket, and if L equals the label associated with the ith example in the sorted order, it gets +1. So this is like a counter of the number of examples in the top K which have label L. I guess that everybody understands, if you don't, the principle of KNN classification. I guess this method is very easy to understand and very easy to implement, and most of you would implement it immediately. But so if there are questions, tell me, and if not, let's switch to the paper, and you should be able immediately to start talking about some advantages and disadvantages of the K nearest neighbor algorithm. And we have mentioned one, so please go ahead.
Advantages compared to what? Compared to n neighbor?
Let's say that, okay, you don't know, at the moment you do not know any method for classification. So think about, maybe you have some idea how deep nets work. So maybe, or a classification that would require density estimation and then maximum posteriori calculation. So think about this as what we are now doing here we'll be talking about properties which are important for let's say classifier design. So I will write the first one, and it seems that it's extremely easy to implement. Yeah, easy and fast to implement. So that's good, but of course that's good only if some other properties are satisfied. Like, okay, we don't implement certain algorithms only because they are easy. So some disadvantages in this. Can someone come up with slow? Yeah, okay. So now exactly, Alexei writes slow. So we'll touch that and some part of this. So actually slow in the trivial implementation, but the k nearest neighbor is actually super fast if we do it cleverly. So efficient implementation. And this is one reason why the k nearest neighbors or nearest neighbors are still used very often. They are very fast. Yeah? So what we'll have to talk about is how to make k nearest neighbors fast. So the second thing, which might looks like it requires a lot of memory. And again, we'll find a method which makes it actually very compact. The other big advantage is that it can classify easily any number of classes. So you can have one class, you can have hundreds of classes, and both these things, you can be sublinear in the number of classes. So what I mean by that, you can have the number of classes C could be really, really, really high, and you can find your nearest neighbors faster than the number of classes, and it will come from this efficient algorithm. Now, can someone, and you might be able to come up already with the answer, can someone think about by far the biggest disadvantage?
Maybe that we need a lot of training data.
No, not really. This depends on many things. We'll see. Okay, so we can say, okay, okay, training data size. Okay, we'll touch this, but that's not the key. Problem is already in the assumptions.
Maybe the problem is that sometimes we need multiple evaluation functions or the distance functions.
Exactly. Well, I will rephrase it. Where do we get the D? Yeah. And that was for sort of 40 years the killer. And sometimes so where does the distance come from? And the simplest example where this, so people would use Euclidean distance, but for instance, if you want to classify our own, like our common problem, the males and females based on height and weight, and you switch your measurements from metric to say feet and pounds, and your nearest neighbors change. So that just trivial rescaling of various measurements could influence the nearest neighbor. This is now more or less can be addressed with deep nets, because they can be used to train to find a very good space that the nearest neighbor can operate in, and there's something called metric learning, and this is the only thing learning. This is something we'll not cover today. So one thing that will cover all of this, and let's start. The only thing we'll assume that we have some good way of obtaining a representation where the distance is meaningful. So we'll start with an example. So this is an example where we have two classes. They have equal priors in this synthetic model. The one class is a Gaussian in 2D, centered at 0, and the second one is like a, let's say, noisy circle, like an annulus, or you can think about it as a circle with a Gaussian noise in the radial direction. The Bayesian error is 0.026, so 2.6%. Anyone remembers? Anyone remember? Alexei had something about the error, and we'll touch that as well. Yeah, there's an error. There's a problem with the error of the nearest neighbor, but we'll come back to that. So, anyone remembers what is the Bayesian error of a classifier? So this is the error of the optimal classifier according to the Bayesian decision task. So because
isn't it? Oh,
yeah,
isn't it just the number of false classifications over the total number of samples?
You can think about it as the limit if you do this, but it's the error of the best classifier. So in this case, because if you look at the bottom picture on the slide, you see that the green and the red distributions overlap. So if you get a sample from the overlapping region, it's impossible to know whether it's green or red, and some error is necessary. And we know that for this case where we have the same a priori probability, we can go for the maximum of these two curves, which are conditional probabilities for the second and first class, which are now proportional to the a posteriori probabilities. So the error of the optimal classifier is like what is in this always on the minimum of the two curves, and it's 2.6%. So let's see what k nearest neighbor does in this example, where we chose to use Euclidean distance without any justification. And we see that the errors are actually quite good. So we know that the error is 26%, the optimum 2.6%, and our classifiers have like the best one is for this particular training set. The error is 3%, so it's very near. So it seems it's doing quite well. Okay. Now, of course, the results depend on the training set. The errors are random variables. Yeah, we can get every time you draw a different sample for the nearest neighbor, you will get a different result. This is in principle true for every single classifier. So we see that these three, T1, T2, T3, they are all training sets with 100 points each. And the error range is between 38 and 43.8 and 4.4% for K1 and 3.0 to 3.6 for K7. So it's very close to the optimal result. If we look at the whole table, we see that for 1,000 points and 69 neighbors, we are very, very close to the optimal result. You see, we had to be more precise here. The Bayesian error is 2.56 and we get to 2.6. Now, one can prove that, okay, so if you are, we'll get to what can be achieved with the nearest neighbor classifier, and there will be a surprising result, which is really surprising, that the error, even for n going to infinity, is bigger. So error of nearest neighbor is greater than error of Bayesian, which means optimal classifier. This is somehow surprising, because if your n goes to infinity, for instance, through maximum likelihood estimate, you can estimate exactly, okay, correctly the parameters of the distributions if you know the parametric form, and then you will get the error equal to the Bayesian error. You will get, but here there is some gap, and that will be explained. Okay, so if we summarize here, we have it's a very good baseline method. The base error is lower than the nearest neighbor classifiers, but at most the nearest neighbor will go to twice the Bayesian error. So that's actually quite a tight bound. It can be speeded up, and we'll talk about that. We'll show that it can be, the training set can be processed in a way that does not require that much memory. And one thing that we'll not talk about is the problem of constructing the optimal metric. Okay. So finding the nearest neighbors in a set of points is a very common applied problem. So I don't know, if you switch your mobile phone, it tries to find the nearest neighbor base set. If you are, I don't know, looking for a taxi and you would have to walk to a rank, you will look for the nearest taxi stand. There are many practical problems where nearest neighbor is very important. So it's not only for classification, it's a classical problem in computer geometry. And I will explain one method, and that's the KD3. There are other methods based mainly on hashing, but okay, we cannot explain everything. And we'll see that the methods are sublinear, which means that you find the nearest neighbor faster than by scanning the list top to bottom and finding the nearest neighbor. And we'll also, okay, fine. I will skip this Voronoi diagram. You can look it up in Wikipedia. So in up to 3 dimensions, you can optimally simplify the nearest neighbor problem by removing certain points using the Voronoi diagram, but that's beyond what I want to talk today about. KD3 for finding nearest neighbors. So imagine you are given a list of points and we'll want to prepare a data structure. That will take us some time, the preparation, and we'll recover the time while searching for nearest neighbors. So normally you will get your training set and you will prepare your KD3 once, and then you'll be then the things will be reused many times, and the KD3 based nearest neighbor will be used many times. So how does the KD3 work? Maybe you can think about a binary search in 1D, but here we are in many D. We are showing it in 2D, but the KD3 construction works in any dimension. Yeah. So we take the points, we choose a direction, dimension. Say we choose x1, and let's say x1 is the horizontal direction. We take the median, which 259,487 is 7, or well, actually, we could have chosen anything between 7 and 5. And we split the data into 2 subtrees based on the value 7 from the 2. Then the other direction is chosen, and in each subtree, you take the median. So 3, 4, 7 was the x coordinate, y coordinate, 4 point we do on 4, and split until we get the leaves. So this is a very short tree here that you have on the slide. We were splitting on a median to get an approximately balanced tree, and if we have n points in the training set, the depth of the tree is log n, and the construction of the whole tree costs me n log n, which is considered an acceptable cost in any context. Like n log n is just slightly slower than n, and it's fine. Yeah. So we have prepared a data structure for this is the KD3. Any question about building the KD3? Will everyone build a KD3 successfully in 10 minutes? or is there, if you have more dimensions, you can swap them, or you can actually repeat a dimension. Often the rule is, there are some heuristics like split the direction along the direction which has the highest variance, and so on. Okay, so now let's have a look at the search algorithm. So now we have a KD tree. Maybe I'll draw it somehow. We have a KD tree, and it splits so we have a KD tree, something like that. And I'll do it in a way that the points are in the inside of this. So this would be number 1. So this will be level 1, level 2, level 2, level 3. Maybe level 3 here. 3. Now, my test point is usually a point that is not in the training set. So something like that. So how do we find the nearest neighbor in the KD tree? The red point has some X and Y coordinate, say in 2D. We start at the root of the tree. That's, let's say, at the root 1. That's testing in the X direction, not the Y. And we have 2 subtrees, and we went left because our red point is on the right. Now, we also noticed that every point in the left subpart, and this is important, has at least distance d1 to the border. So d1 is a lower bound on the distance which is valid for every point in the subtree. Now we come to decision 2, which is done on the horizontal direction. This is the 2 here, and we are going up, and that's it. We reach the leaf. In the leaf, we see there's 1 point, and we are computing the first distance. Notice that in a classical search, if you have n size of the training set, n times d would require, d is the dimension, so you would have to compute the distance for every point to find the nearest neighbor in a standard simple algorithm, and n is the number of points. Here, at every level, we only did 1 comparison, and we did log n. We found a point, and we established some distance, let's say star 1. Is this the nearest neighbor?
Was that a question or?
Yeah. So is this this is a question. Is the
As far as I can see, no.
So it's not
necessarily.
Not necessarily, exactly. So what do we know? We know, so D1 was an upper bound, sorry, lower bound on all the points here. This D1 is an upper bound on the distance to the nearest neighbor. Whatever is outside this circle cannot be a nearest neighbor. So in the root, we established a first approximation of our distance to the nearest neighbor. Now, some parts, like this part, doesn't have to be searched at all. Maybe if I draw it a little bit like this, more carefully here, yeah? So it cannot be either here, because everything in that part of the space is further than the distance to that plane, and it doesn't intersect the circle. So after the first one, we know it could be only here, here, here. But how do we know that computationally? So let's say when we were going down, we went right and up, and here we had a lower bound d2. So we know the lower, so if dx, if this distance in the subtree is greater than d star, we can cut that tree completely. And what we'll do, we keep a priority queue of subtrees, and we'll go into the subtree that has the smallest lower bound. Okay, in this case, we'll go to the left, up, and we'll end up, and then we'll go up again here, and we'll find a point called X. This is this one here. Aha, this is nearer. We'll reduce the our upper bound. This actually rules out this part and this part, and the only remaining subtree to check is, I think it's this one here. I'll make it as a triangle. This is this triangle point. That's too far. We measure the distance here, like that. This is greater, and we are done. So what we have seen here is an example of something called, which is used in many other parts of computer science, branch and bound algorithm. So we were searching using a tree search for the nearest neighbor. The tree, which we can look in the right, is like a symbolic thing. It had a d-dimensional embedding. We found the root, the leaf in which we belonged. And as we were making comparisons on the border, on the inner nodes, which half plane we belong to, which required only one comparison, we remembered the distance to the separating plane, and that was the lower bound on the distance in the subtree. So these were the branches which had the lower bounds, and as soon as we reached a leaf, we possibly updated the upper bound. And once the upper bound became smaller than many of the lower bounds, we could avoid checking those parts of the tree. Of course, if you have 10,000 points from a big distribution, the picture will look very different. Here, we had few points and we had to check 3 or something like that. So, do you understand the algorithm? This is an application of branch and bound, a KD3D. We are using like the data structures we need is a heap, priority queue for keeping the list of branches. It's a heap of branches because the only thing we need to know where is the lower bound, the smallest, and that's where we go first. Okay, let's assume that it's okay. One question we didn't touch, and it's a very complex one, the complexity of this algorithm. So we know we were able to build the whole thing in n log n. We know that to get the first estimate costs log n. But how many branches will we have to visit? And actually there is no good answer to that. because everything depends on the distribution of the points. There's this nasty thing that if you have randomly generated points in high dimensions, they are sort of like all equally distant to each other, and this method becomes inefficient. So classical textbooks say it works to dimension D up to 10. In computer vision, it's often used in much higher dimensions, sort of like 128. And the point is that it's very unlikely for data, high dimensional data, to be randomly, uniformly distributed in the space. And often, if you have very high dimensional data, you will find out that their effective dimension is much smaller, for instance, 10. So what it means that you are measuring 128 numbers, but everything lies in a 10-dimensional subspace. So 10 numbers would have been enough to describe the situation. Okay. So now, if we come back to the properties, we see that we have now something which is fast, because the speed is something like a couple of times log n. There are libraries, most popular of which is called FLAN, that implement something slightly more complicated, because one KD tree could be very unpleasant for certain points. If you have multiple trees, a forest of trees, it becomes very likely that at least in one of them, the nearest neighbor you recovered was the right one. And this this is nearest neighbor is the NN. We know this abbreviation. F is fast, and I think L is library, and A is one word that we didn't talk about. It's approximate. So we know that our classifier will not be perfect anyway, and very often in nearest neighbor, if we have something like that, and the other class would be here, and our point to be classified is somewhere here, we don't really need the nearest neighbor to classify correctly. And it turns out that if you are happy with approximate nearest neighbor, you can be really fast. And you can be really fast for any number of classes, because really the complexity of the method does not depend on the whether all these examples in the trainings that are from the same class, or whether each of them represents a different class. This is a very rare situation, and together with tree-based classifiers, this is the only method which is suitable for a very, very large number of classes. Okay, now we'll touch the problem of memory. Even the example that I showed here before, this one, you can imagine, one can easily imagine that if you have lots of points here, you don't really need all of those points to classify correctly. Like if the decision boundary is something like that, all of those guys here are quite needless. Just maybe these, and maybe this one is needless, and this one. So if I only keep 5 points, which this one, this one, this one, and 2 red ones and 2 red points, the decision boundary will be almost, okay, I still need probably one more red point here to keep it the same. So if I have this point, we have 6 points, and the decision boundary will be something like this. Here I have to have something like this. Classifying the other ones correctly. And so this idea that not all points are needed is the core of this simple, very simple algorithm called condensation algorithm. And I think it's very easy to understand. So let's see. We'll have a training set T. These are all the points we have. And we start with B being a very long list, almost all samples but one from T are in A, and one sample goes to T. Now we proceed as follows. Classify samples from B using one nearest neighbor with a training set A. If B is misclassified, move it from B to A. So, and then do this until you run through B and everything is correctly classified. So by definition of the stopping criterion, step 3, the final, let's call this, we had a T before, and now we have the T prime, which is some subset of T. Okay? So it's clear that, let's say, we'll say that T is T prime plus, okay, union removed. So we know that all of those points which are not in the T prime, they are correctly classified with the T prime, all the removed points. This is not the minimal subset. I think the optimal solution has to be done through the Voronoi diagram, and that's the complexity of calculating it in dimension higher than 3 is prohibitive. So simple algorithm. Any questions about the condensation algorithm? Okay, no question. So let's assume that you got it, and we can move to the, so this is an example here. So this is an example where you see some two-dimensional mixtures of Gaussians. And I'm not sure how many, I think it's 100 points from each of the distributions. And you end up with like 3 on one side and 4 on the other side. So a huge reduction. Okay. Now we are touching the problem, the final problem that we would like to talk about. So memory can be fixed by condensation. We know that. Slow can be done by fast nearest neighbor method. This could be FLAN or something based, and we can't cover everything here, something based on locally sensitive hashing. I'm just saying this so that you are familiar with the term. So there are some fast methods, and can be this, the method that we just introduced for memory reduction called condensation. That's a very simple algorithm, solves the memory. Training data size. Okay, before we go to the error, so the question is, why should nearest neighbor overfit? We can easily use cross-validation to set K, and with larger Ks, there is no, okay, it does have, well, we can, through cross-validation, we can find a K which does not overfit terribly. And the size will depend on the data and the distribution. So I think that's in practice not a problem, but the remaining problem is the error. And it seems counterintuitive, at least it seemed to me when I first noticed it, that if you have a nearest neighbor, and I'll do it in 1D. So we have a blue class, say, with high density here, and a red class with high density in this part of the X space. but few here. Maybe the underlying distributions look like this. So, and the interesting thing is, so this would be like P x given 1, and this would be P x given 2, and let's say that P2 equals P1 the prior, so that we don't have problems with the prior. Now equals 1/2. Now it seems so. An interesting result says the error of a nearest neighbor is not converging to E epsilon by base, even when n goes to infinity. Now, this is, why is that? I'll leave these theoretical calculations here, and I'll show it on this picture. This is the same picture that we have on the piece of paper, and we'll have a look at some point here. So let's see at the point S. So we have, from the two conditional probabilities, we have calculated P1S and P2S, the a posteriori probability. So what is the optimum decision for a Bayesian classifier? If we observe something around S, some value around S, the optimum is to go for class 1, and my error will be the probability, a posteriori probability of class 2, which is 20%. I think so far all is clear. Now, let's see what happens if we run nearest neighbor. Yeah? So what happens, and I will now extend this, like this is the area around S. Now, if we have a lot of points for n going to infinity, 4 things can happen around here. The point we are testing is from class 1 or from class 2. And so this is the sample. This is what we are classifying. And now we ask what is happening with what is the nearest neighbor. It can be again from class 1, class 2, 1 and 2. So the correct classification is 2 and 2 and 1 and 1, and these two cases are actually mistakes. So now let's see how often these two things happen. So looking at the graph in the presentation, we see that this place has the probability 8 to, so this is 0.8, no, is it? Yeah, and this is 0.2. Now, because of the same density in the training set here, again, this is 0.8 and 0.2, and this will happen with 0.8 and 0.2. So in the end, we have 0.64 and 0.04, and in here we have 2 times 0.16, 0.32. So it's only correct in 68% of cases, and it makes a mistake of 32%. Whereas the base error, so this is the error of this thing is epsilon nearest neighbor, and epsilon base here is 0.2. Yeah. So quite the difference. What's the problem? You can think about this scheme as sort of randomization. So we know that if we observe S, we have to go for the maximum a posteriori. Yeah? And the nearest neighbor is not going always for the class, which is more common here. It's switching between the more common and less common class, and the errors are their error is higher. If we look at these two numbers, like let's say that the 0.8 is A, this is the probability of the class which is higher, and B, then the probability for Bayes, the probability of correct answer is A, and the probability of a mistake is B. Now, for the 1 and n, the probability of a correct one is A times A plus B times B, and the mistake is 2 times AB. Now, two times AB is higher than B, because A is bigger than B. Therefore, okay, we can say something like this: A is greater than B. A plus, I don't know what do we want here. Okay, what we want to prove is that 2AB is greater than 1, and that's because A is bigger than 0.5, because it's bigger than B. Yeah, so this is the difference. But again, the difference is just like not because 2A is a bit greater than 1, but it's smaller. This is great. 2A is greater than 1, so the error of the nearest neighbor is bigger than the Bayesian, but it's smaller than 2. It's not the error of the nearest neighbor is at most twice. So if the base error is very small, like 1%, the base error is the error of the nearest neighbor is at most 2%, so it's not too bad. So this is the more general result for K-classism. And here we see for this particular example the difference between the base error, which is the black curve, that's just the minimum of the two, and the cyan is the error of the nearest neighbor. So at 50, here, there's no difference at the point where both have like 50-50 is the worst case situation. And for the very clear-cut cases at the end, it's also almost the same. But at some intermediate points, the difference is substantial. And okay, this is more a generalization of the result for R classes. We don't have to go through that. And I want to introduce, okay, maybe for K and N, the result is a little bit better. So this is the base error, the best achievable. This is the error of the nearest neighbor that we just said that could be at most twice the Bayesian, but divided by square root of the number K. So if K is 100, square root is 10, and then this term is very small. But we have a better option, and that's the edit algorithm. So the edit algorithm can fix this problem that the error of the nearest neighbor is not converging for even large training sets to the error of the Bayes classifier. And the edit proceeds like this. We take the training set and split it into two subsets, say equally sized, they are disjoint. We classify samples in B using K and N from class A, remove all samples from B which have been misclassified, and keep the rest. Output is the B, and that classifier has an error in the asymptotic case, which is like this is indistinguishable from a Bayes. So let's get some numbers that we had there. The edited error is edit bias, so that was maybe say 2.6%, and here we have something minus, say, error of base, so something like 0.02, and this might be 1 minus 0.0, say 3. So this is something like 98, 97. So before we said that the error of the nearest neighbor was possibly 2 times error of base. This is 1 and n, and the 2 now becomes 98 over 97. Yeah. So that's almost 1. So we removed 2 to 1.1 or something like that. Now to explain the algorithm, what have we done? Which points have been left for the 1 and n classification? These were the points in B that were classified correctly. So which are removed from B are those points which were minority. So actually B in the reduced training set, B cleaned from those which were misclassified. We just have the majority class. So if we go back to this example that we worked on, all these red points here, which are in the minority, will be removed. The same thing will happen with the blue points. So our classifier will become the optimal classifier, almost the optimal classifier, which will say blue here and red here on this from this 50-50 point. And before, the nearest neighbor was like a classifier which was saying, okay, red, a little bit of blue, red, a little bit of blue, and so on. Okay, so if we look at it overall, the nearest neighbor comes out as a pretty competitive classifier if we can find a good space in which to measure the distances. And besides deep nets, we'll have one more lecture on this. We'll have a lecture on something called LDA, linear discriminant analysis, which also finds nice subspaces for nearest neighbor. So the nearest neighbor is sort of like onion. You are peeling off and you find new layers. What looks at the beginning as the main advantage that you can easily implement it and do some testing in 1 hour. If you did that, you would have slow method with high memory requirements and higher error. But if you spend some time on efficient implementation of the nearest neighbor, you get something super fast for arbitrary number of classes, and you don't even have to have high memory footprint if you use this compression algorithm, the condensation. And if you want to use it, you don't have to have this problem with this non-convergence to the optimal classifier if you use the editing algorithm. So that's a summary. That's the final slide of the lecture. And do we have questions, please? So either we have some bad weather today, or everything was clear and understandable, which hope is the case. So last call for questions, or? Okay, fine. Thank you, and that's the end of the lecture.
Thank you, Professor.
Thanks.
Thank you.